Hi, my name is Vishal and I'm a data analyst transitioning into machine learning research, and this is my channel where I'm documenting my entire journey. I'm passionate about tiny models, resource-constrained research, and understanding deeply how things work. And today I'm going to give my summary for the Tulu 3 research paper, Pushing Frontiers in Open Language Model Post-Training from Allen AI and University of Washington. This is a fantastic paper, I think one of the best papers that I've ever read. It is certainly one of the most, if not the most, information dense while being accessible papers. The way I, came away from this paper was feeling that this could be a curriculum for an entire, graduate program. And it's structured more like a textbook than it is a paper, in the sense that it's hard to kind of summarize the whole paper. You can summarize kind of the individual chapters. So because of that reason, I'm not going to have my normal main takeaways that I do for research paper summaries, because there's just too many things, too many important details that I can't remove. So instead, I'm going to start at a high-level overview. Then I'm going to do an overview of the Tulu 3 recipe and go a little bit deeper and look at some of the key highlights. And then we're going to go step by step, stage by stage, and do our main takeaways for each of these stages of the Tulu recipe. So stage 1 is Tulu 3 data, stage 2 is supervised fine-tuning, stage 3 is preference tuning, and stage 4 is their innovative reinforcement learning with verifiable rewards. And then I will walk through the evaluation framework and end with the closing sections of, discussion, future work, and so on. One thing I will add as a bit of a disclaimer is that I don't know how to do reinforcement learning, so I'm not familiar with that concept. So stage 4, I do my best to understand the concepts to my ability, but is certainly the most lacking section of this video. All right, so let's jump in with the overview at a high level. What are their contributions? First, they present an extensive guidance and tooling for evaluation, decontamination, and recipe design when it comes to post-training. They introduce new synthetic instruction data. They show that they can scale preference data with on-policy generations. They present an RL-based method where the model gets a reward only if its response is verifiably correct. And this reward verification is done by a function, a verifier function, where you can do things like a simple extraction from the response instead of a reward model. And they're presenting advanced infrastructure details and code for large model training. They scale everything all the way up to 405 billion parameters. These are the overall steps of what we call the Tulu 3 recipe, or what they call the Tulu 3 recipe. The first thing is they identify core skills. And so they're basically saying, where do open source models lag behind state of the art, just in general? And so they have a baseline where they find that these skills are lacking on different benchmarks. Then based on those skills, now that they've defined those skills, they can curate the prompts. And this is, one of the most, if not the most important part of the pipeline. And they really try to emphasize how important it is to curate the right prompts. They use public data sets. They have synthetic instructions with something called personas, which we'll talk about. And they are rigorously decontaminating their data sets so that the training set is not cheating on the evaluation set. Then we go into the actual training pipeline. So we have supervised fine-tuning, starting with a Llama 3.1 base model. That yields Tulu 3 SFT. And that process also involves another layer of data mixing that we're going to walk through. Then they take the SFT model and they do DPO on it with on-policy and off-policy data to yield Tulu 3 DPO. And then they perform RLVR on their DPO model to get the final Tulu 3 final model. In this process, throughout this process, they are checking performance on their development evals. And then at the very end, once they have their final model, then they check the performance on a hidden, held out set called the unseen evals. So ultimately, they are trying to do their best to make sure that they're not overfitting and that their model is generalizing to unseen data. There's 3 different types of data at a very high level. Supervised fine-tuning has prompt completion instances. Preference fine-tuning has preference data where you have a prompt and then you have chosen and rejected pairs. And then reinforcement learning, you have some kind of verifiable reward, verifiable verifier function. So you have a prompt and then you have some kind of function that verifies that the response is successful. This is a quick overview of the models involved and their different names. So the base models are the Llama 3.1 family of 8 billion, 70 billion, and 405 billion. And then the different SFT and DPO models that are released are listed here. And then they also have a final model, which doesn't have a kind of suffix. And then they have their reward model as well. Tulu 3 pushes the boundaries of research in post-training and closes the gap between open and closed fine-tuning recipes. With Tulu 3, we hope to uncover which paths for the open source community will lead to success and which do not by reporting negative results. Tulu 3 is not just an artifact, but a comprehensive suite of data and tools designed to advance the frontier of open post-training. So I highlighted this reporting negative results because I found it very helpful. Like, they've done all this work to find out what works, and to find out what works, hopefully you found out what doesn't work. And I think presenting that information so that the rest of us can start building some intuition around what works and doesn't work under what circumstances, I think is a great contribution to the community. And I would love to see that happen more and more. This is a quick snapshot of where this is heading. And the result is that Tulu 3, their final model with SFT, DPO, and RLVR, trained on Llama 3 base models, outperforms all other open weight models in its size category on our development eval suite. Compared to closed models, Tulu 370 billion even surpasses them, such as GPT 3.5 Turbo, GPT 4o Mini, and approaches the performance of Claude 3.5 Haiku. And I think that's really interesting to see, and we will concretely look at that, you know, the 70 billion parameter model is reaching performance of Haiku and these other closed models. And this is what we look at here. So we have three sections to this table. We have the 8 billion comparison, so we have Tulu 3 8 billion, Qwen 2.57 billion instruct, and Llama 3.1 8 billion instruct. We have the same ones for 70 billion, for our corresponding ones for 70 billion, and then we have our closed models. And if we look at the overall average, Tulu 370 billion has 76.2% overall, whereas Claude 3.5 Haiku is second place at 75.3%. So right off the bat, that's really cool to see. And then if we look at the different individual benchmarks across these 6 skills, we can see that there's some skills, you know, Qwen 7B is higher, for example, in math or human eval, but most of the skills and most of the benchmarks, Tulu 3 8 billion is higher. 70 billion, when it comes to individual skills, there is a lot more competition, but you can see that the average is overall beating out the other models. And just let me see if I can move this for a second just to see that we have our 6 skills. IF means instruction following. This is a comparison of the Tulu 3 models to other models that started with a different base model. So Magpie, Gemma 2, Minstrel 8B. And you can see that Tulu 3 8 billion is pretty competitive, right? It's second place overall. Is that right? Yeah, second place overall. And in many of the categories, it is competitive with these other models. And then we see the same thing for 70 billion. Other models that started with different pre-training. And then we have our 405. And in this case, we're also comparing it to DeepSeek v3 and GPT-4o. And if we look at the averages, it's beating out, the RLVR version is beating out DeepSeek v3. And it's competitive with GPT. Just to go back to this slide, these are not different pre-trained. These are both Llama 3. All of these are, I think, except Qwen 2.5, all of these are Llama 3.1. And so this is a comparison of models that started with the similar pre-training base model. All right, so that's a high-level overview, and we kind of, you know, get out of the way the final result, right? Which is that this Tulu 3 recipe yields solid results, beats other open source models, competitive with some closed models. So now with that out of the way, we can really dig in to the recipe and try to understand like what's actually going on. The first thing I want to highlight is that they did not examine scores on our unseen set when developing our models. This is, might seem like a obvious point, or maybe certainly not trivial, but it might be well known. But they wanted to observe how much they have overfit to their evaluations in the decisions around data mixtures, algorithms, and hyperparameters. So all of their decisions are empirical, and if they make a data mix change, the only reason they're going to make that change is if it improves the eval suite performance. So they're constantly using the eval suite as the guiding metric. Because of that, there's a chance you could overfit to it. So the unseen eval suite is very helpful because it lets them know, did their decisions actually generalize, or were they just decisions that fit to maximize the eval suite benchmark or benchmarks? So we're going to start by talking about how they identified the core skills. What they did is they started with the Llama 3.1 model, and they had trained it on the Tulu 2 data mix, and they measured the performance, and they looked at where it was lacking when you compared to open source models and closed models, and that's how they identified these core skills. So we identified the skills that were lagging behind state-of-the-art models using Llama 3.1 trained on Tulu 2, not Tulu 27, as our baseline. Targeting each of these skills in isolation, we collected high-quality, publicly available datasets and created synthetic datasets. So one thing that we're going to see is that this balance between targeted skill performance, such as math, coding, instruction following, versus general knowledge and general chat performance. They, as part of their evaluation suite for these 6 core skills, they newly created 2 eval datasets, which we will briefly talk about near the end. All right, so that's step 1, identify core skills that we want to maximize. Step 2 is now curating prompts and then going into our 3-step training pipeline. So here are the 4 stages of post-training. Stage 1 is data curation. Stage 2 is supervised fine-tuning. Stage 3 is preference tuning. And then stage 4 is reinforcement learning with verifiable rewards. The key contributions of our pipeline lie in the improved data, methods, infrastructure, and rigorous evaluation. So some key points about prompt curation. They surveyed many available open source datasets, and they've linked a Google Slides or Google spreadsheet in the paper. I think it's on page 11. They analyzed their provenance, which is the licensing. And if they didn't like the licensing, or if they saw any legal issues like they did with ShareGPT, they did not use that data set. They decontaminate their data, so they're not cheating on their eval suite or unseen suite. They curate synthetic prompts that target core skills, and then they studied the dataset impact on development evaluation suite. So 2 things they found is that targeted prompts improve core skills. So if you want to improve math performance, you got to give it math data. The second thing they saw is that real-world queries improve general chat capability. So getting real user assistant interactions as your prompt response pairs improves general chat capabilities. And they highlight the wild chat dataset. For stage 2, the highlight for creating a multi-skill SFT dataset is to refine the distribution of general and skill-specific prompts by training on various data mixtures. So there's always this balance of trying to maximize skill-specific performance with general performance, and not forgetting general knowledge and language understanding in favor of skill-specific performance. And how they approach this is that first, they train models just on a specific skill. So they have a math model, they have a code model, they have an instruction following model, and they establish a skill-specific upper bound on the eval suite. And then that's how they know, like, that's our theoretical maximum. And then they mix in general data to diversify the data set, and that's going to decrease the skill-specific performance, but now they know what is the maximum that we can try to improve and iterate upon to achieve. So I thought that was a very interesting concept, that single skill upper bounds in the evals can give you a sense of what your theoretical maximum is. Stage 3, they curate an on-policy preference data set. So that's one of the highlights. They use off-policy data as well. And on-policy means that they're using their Tulu 3 SFT model to generate completions. They also use other models as well, and those other models are the off-policy generation. They use synthetic data to generate preference labels, and they binarize them to create pairwise comparisons. And they end up with over 350,000 preference dataset items, and they find that that improves skill performance. Another highlight from stage 3 is their algorithm, which is length normalized DPO, which they find performs best given their compute constraints. And they're prioritizing simplicity and efficiency. So they're balancing performance with efficiency and compute constraints. And then stage 4, they have an RL approach that targets skills with a ground truth outcome. So something that can be verifiably correct or incorrect, such as a math answer or a certain constraint that the model needs to follow given the instruction. The reward value that comes out of a reward function, not a reward model, is non-zero only if the completion is successful. Otherwise, the reward value is 0. And then stage 4, training infrastructure innovations. They have a asynchronous RL setup. They do LLM inference via VLLM while learners perform gradient updates concurrently. And this scales to 405 billion parameters. And finally, all stages use the evaluation framework Tulu 3 eval. And this is an open evaluation toolkit that is posted publicly on GitHub. Okay, so that's a high level kind of highlights of what are some key things that worked across all 4 stages. So now we're going to go deeper and we're just going to focus on stage 1, which is talking about curating these very important prompts. They say that prompts represent the diverse ways users may interact with models and served as the essential component for all post-training stages. So the importance of curating the right prompts, that was something I really came away with. Ultimately it comes at looking at your data and making sure that you are giving your model the best chance to perform well in a general setting. Here are the prompt curation takeaways. Diversity of training data is critical for eliciting models generalization and avoiding model forgetting. And these are the data sets that help diversify the training data. Complex reasoning, coding, and precise instruction following benefit from mixing in additional data that is specific to that skill, and these are the data sets. Using persona-driven methodology to generate synthetic data yields better performance, and so they do this for instruction following, which is IF, math, and coding. Using constraint types to verify precision instruction following is their approach. Constraint types is something like a part of an instruction that says include the word banana 5 times, or only use capital letters, or only use lowercase letters, and so on. There's a list of 25 that they reference from a different paper, which we'll look at a sample from. And then later on, when they make their own eval dataset, they source their own custom 52 constraints. And these are all, again, verifiable constraints. And finally, non-compliance and safety prompts are sourced from open datasets / synthetic generation. So let's look at the breakdown of their dataset. So here are the datasets that promote diversity. We have scientific literature understanding, table-related tasks, mathematical reasoning, coding, and multilinguality. And then we have verifiable instruction response pairs, which is the persona IF. And there's a number of other ones that I haven't gone through, but you can see there's some other persona ones that we'll take a look at. Something else I wanted to highlight is that the overall count of the dataset prompts is high, and then some of them are used in SFT, some of them are used in DPO, and then some that are used in SFT are also used in DPO, and we will talk about that unused used mix in DPO when we get to that section. So when it comes to synthetic data generation for these constraints, we start by manually writing 1 to 2 example instructions per constraint. For example, number of words that the model has to include in its response, resulting in a total of 33 verifiable instructions which we used as seed prompts. We then generate new instructions using GPT-4o, given a data synthesis prompt, persona, and a single verifiable instruction as an example. So this is an example of what a persona looks like from the paper Scaling Synthetic Data Creation with 1 billion personas. And here's a persona, a machine learning researcher focused on neural network architectures and attention mechanisms. Or a pediatric nurse who is responsible for administering injections to children and ensuring their safety and comfort during the procedure. Or a mobile gaming enthusiast who enjoys competitive multiplayer online battle arena games and is interested in exploring different titles within the genre. In that paper, which I have not read, I've just skimmed to look for good figures to include in this presentation, they have this example about how you can have the same prompt, create a math problem with the following persona, but you can change the kind of description and then you can change the result based on that. So for example, create a math problem with the following persona, a linguist with a particular interest in the intersection of language and social interaction. And that gives you this generated text. Now it says create a geometry problem with the same persona, and it goes into talking about geometry related items. And then it says create an Olympiad level math problem with the following persona, and then it kind of ups the complexity and difficulty. So quick snapshot at what personas are and how they interact with the generated text. So this is the instruction they use for synthetically generating instruction following prompts. They tell GPT-4o to create a verifiable instruction that the following persona might ask you to do, and then they give them the persona. An example of a verifiable instruction could be, and they have one of their 33 seed prompts. And then in their notes, the second one is of interest. The instruction should contain all the following verifiable constraints, and then they put their list of constraints. So that generates an instruction. Then they feed GPT-4o that instruction and say provide a response to the given instruction while satisfying the constraints. Repeating again, note that you should follow the instruction precisely and satisfy all the constraints. And so that's how they get their precise instruction following synthetic data prompt response pairs. In total, they have about 30,000 verifiable instruction response pairs, which they call IF persona SFT. They also generate prompts from randomly sampling the Tulu 2 SFT mix, and then they add these constraints and generate prompt response pairs. They call that set IF augmented, and those are only used in the last two stages of training. These are some examples of the constraints. So for example, include keywords 1, 2 in your response, or in your response, this letter should appear n times, or answer with at least, around, at most n words, or n sentences, or there should be n paragraphs. Other ones, entire output should be wrapped in JSON format. Give two different responses. Responses and only responses should be separated by 6 asterisk symbols. And then, so these are all things that you can, with regex, you can check, right? And you can get confirmation on whether this was passed or not. Again, leading to that verifiable, precise instruction following approach. That's for instruction following. For coding and math, we generate Python programming questions that are solvable by entry to medium level programmers. We zero-shot prompt GPT-4o to generate problems that are unique and specific to a given persona input. Having generated the problems, we then generate multi-step math solutions using GPT-4o and Python programs using Claude 3.5 Sonnet. So interesting to see that they use different models for different solutions. And similar to the instruction following, we have the prompt to create more prompts. So they give it a persona, and then they give it some instructions on how the response is formatted. And then they take that generated math problem and they say, hey, given this problem, provide a solution and make sure the final answer is in between dollar signs and says, I hope it is correct. Again, this allows easier extraction to confirm whether or not this was answered correctly by the model. Code completion, similar. Persona with some notes on what this type of Python programming question should be. Take that Python code problem, add it here, provide a solution to the given programming question with some additional instructions. And again, they repeat this process for coding as well as for math. All right, now looking at prompt decontamination. So again, they're trying to make sure that they don't cheat and they get real generalization results. So 8-gram matching, they found, yielded the most useful results. So any sequence of tokens where 8 tokens match. What does it mean that a dataset is contaminated? It means that it's more than 2%, contains more than 2% overlap between training and eval datasets. So more than 2% of the instances in the dataset have that 8-gram match between training and eval datasets. If a dataset is contaminated with unseen evals, they remove the entire set. If the dataset is contaminated with the development suite of evals, they remove the entire training set if the performance is not impacted. If the performance is impacted, then they only remove the specific instances that are contaminated. While embedding-based methods can in principle identify non-trivial contamination, like that due to paraphrasing, we found it difficult to distinguish mere distributional similarity from actual paraphrasing. So this was really interesting to see that, again, them highlighting what doesn't work. They tried embedding-based methods. They found that it's not effective enough to differentiate just similar language from actual paraphrasing. These are examples of their decontaminated datasets. This is the percentage of the dataset that was removed. The largest percentage was for Numina Math, where they removed 11.3% of the dataset. This is an example of their public datasets where there was significant overlap, so greater than 5%. We included decontaminated versions of the first 5 datasets, and then they did not include the last 4 datasets, ShareGPT not being included because it had some legal issues. So you can see that eval code alpaca had 70% overlap with human eval, and so they remove that 70% and they only include 30% of that dataset. So reiterating my prompt curation takeaways: diversity of training data helps generalize and avoids model forgetting. Complex reasoning, coding, and precise instruction following benefit from mixing in additional data related to those skills. Persona-driven methodology for synthetic data generation helps. They use constraint types to verify precision instruction following. Non-compliance and safety prompts are sourced from open datasets and synthetic generation. All right, so that is stage 1. We have now curated our prompts. We have decontaminated them. Now we can start looking at what is the best mix for my stage 2 supervised fine-tuning. We conducted data mixture ablations and explored model merging techniques to develop an SFT training procedure that well balances performance across the core skills we prioritized. So here are my takeaways from the paper when it comes to the data side of SFT. The SFT mix responses for those curated prompts were obtained by filtering existing responses in datasets or creating new responses synthetically. Keep in mind that they identified the lagging skills using Llama 3.1 trained on Tulu 2 as a baseline. The SFT mix is built by combining high-performing skill-specific mixtures, which they call preview mix, and iterating on it to improve skills and decontamination, which they call the final mix. Diverse chat data improves most skills, including targeted skill-specific datasets improves those targeted skills. Safety is orthogonal to other datasets. Persona datasets improve skills. Models generally improve as SFT data is included, as more SFT data is included. And they replace the new line character with EOS token at the end of assistance response and find that it gives a slight bump in performance as well. So this is a distribution of starting from the Tulu 2 in the light pink and then adding intermediate mixes until you get to Tulu 3. The last couple intermediate mixes involve decontamination, so the performance drops a bit. The first 3 intermediate mixes are the results of adding new data sets to improve performance. This is an example of the performance of Tulu 3 SFT models against comparable baselines. So you can see the Tulu 2 8B SFT was 48%, Tulu 3 8B SFT has a 12% increase. When the 70 billion models are compared, there is about a 9% increase. This was a really interesting way to look at their experiments. Basically, they said, what happens when we remove these data sets? Another way of framing that is, how important is it that we keep wild chat, that we keep safety, that we keep persona data, that we keep math data? So they remove those, find the average, and then make their decision. So when you remove wild chat, you get a degradation of skills across the board, except safety. Everything else drops. Safety, when safety is removed, it's a relatively low impact. Interestingly, there is a little bit of improvement for math and pop QA. When you remove your persona data, you also get a drop in those persona specific tasks. So human eval plus, GSM 8K, math, IF eval, all of those drop if you remove the persona data sets corresponding to those skills. IF eval drops by 20%. So instruction following persona based data sets gives a 20% boost in that area. If you remove math data sets, then the GSM 8K and the math benchmark performance drops by 12% and 8% respectively. This is the graph that shows that for everything except truthful QA, adding more data gives a overall higher score. So the average increases as you go from 5% to 100%. GSM 8K increases, human eval plus increases, safety increases. When compared to their Tulu 2 template, replacing the new line character at the end of the assistant with an EOS token gives a 0.4% average boost. However, they kept this new line at the end to be consistent in later stages of their training pipeline. So, going back and just recapping our SFT takeaways, they have both existing and synthetic responses for the curated prompts. They combine high-performing skill-specific mixtures, and then they iterate on it, adding and removing data and decontaminating it to get the final mix. Diverse chat data improves most skills. Targeted skill data improves those targeted skills. Safety is orthogonal to other data sets. Persona data sets improve those targeted skills. Models generally improve on more data. And even though they replaced that new line with EOS token for consistency later on, they kept their original chat template. What about training? So for the 8 billion parameter model, it took them 6 hours on 32 H100s, and the 70 billion took 64 H100s for 50 hours. The base models are from the Llama 3.1 family. Increasing model size and domain-specific pre-training both improve downstream skills. Performance varies based on random seed, and an ensemble, which they call a soup, isn't always best, so they use the best single SFT run. And then sum loss was used instead of mean loss, which we'll talk about in some detail in a second. So here we show that as we increase the model size from 8 billion to 70 billion, downstream skill goes up by 15% for GSM 8K and 22% for math. And then when you use a pre-trained model that had domain-specific pre-trained data, this increases downstream skill as well. So 7 billion to math 7 billion gives you 7% more in the GSM 8K and math dataset benchmarks. Quick screenshot from the Quen 2.5 blog post, which shows that they have synthetic math pre-training data that they use to pre-train their model, and that generates their Quen 2.5 math. This is the data that supports their claim that the best model soup doesn't always get you the best result. So for the 8 billion model, it did, but the 70 billion random seed 456 actually got the best overall average. All right, I want to go into a little more detail on this loss calculation, and this is really interesting. So assume we have two samples in a batch, and they have non-padding tokens N1 and N2 respectively. If we pass both samples into the default transformer's forward pass at the same time, so in this as a part of the same batch, the way the mean loss is calculated is that you add the loss for each token, for each item, and you divide by the total number of tokens. So that is weighing each token equally across the combined item loss. However, if we apply gradient accumulation, which they did, feeding in the two samples separately, computing loss, and then dividing, our loss is instead computed like this in transformers. You have loss of N1 divided by N1 tokens, plus loss of N2 divided by N2 tokens, the sum of those divided by 2. And in the second case, they are weighing each example equally, even though the number of tokens are different. So mathematically, kind of a toy example, let's say our N1, item 1 loss is 1.5, as well as the item 2 loss. Let's say item 1 has 100 tokens, item 2 has 200 tokens. So when we do the first equal weight to tokens approach, which is the batch transformer loss approach, we get Ln1 plus Ln2 divided by N1 plus N2. So we get 1.5 plus 1.5 divided by 100 plus 200 gives us 3.0 over 300. Our loss average is 0.01. If we do the gradient accumulation step with mean loss in transformers, you have the loss divided by the number of tokens plus loss divided by number of tokens divided by 2. So 1.5 over 100 plus 1.5 over 200 divided by 2. Slightly larger now because we are equally weighing this 1.5 over 100 with the 1.5 over 200, and we get 0.1125. I thought of this as an average of averages is not equal to the quotient of the sum of the numerators and the sum of the denominators when the denominators are not equal, as is the case here. Looking at it with code, let's say I have some logits, random numbers, 100 tokens for logits 1, 200 tokens for logits 2. I create some random labels. I calculate the sum loss for item 1 and the sum loss for item 2. And then I do the two calculations. I do the per token average loss, sum of losses divided by sum of tokens, and then the per item average loss, which is loss over tokens plus loss over tokens, that sum divided by 2. And then I do the batched approach. So I combine my logits, I combine my labels, and then I do the batched average loss where I'm giving the combined logits and labels and doing the reduction of mean. And if we look at those results, the per token average, which is our manually calculated, right, with the two sum losses averaged manually, is the same as the built-in mean loss for the batched average. And that's really the main signal that we're seeing, that we want to see here, is that gradient accumulation is handled the same way whether the items are individually processed, as is the case with the per token average loss, with two separate forward passes and two separate loss calculations, versus the batched average, which is the built-in approach that calculates mean loss with one forward pass with both batches. So we want gradient accumulation. We want separate forward passes to result the same batch loss value, because the same loss value is going to back propagate to give the same gradients. If we do the per item average manually, we get a different value than the batched average. So that's going to back propagate with different gradients. There were also a couple papers listed, and I think there's other instabilities that happen with this kind of incorrect gradient accumulation loss calculation. So what are other effects of sum loss? If you use sum loss instead of mean loss for different learning rates, you get a higher overall performance with sum loss, and this kind of confirms the stability that it provides to the gradient updates. And then you also get a more robust to learning rate, average performance, right? Sum loss, fluctuates maybe 1%. Mean loss fluctuates, a little more than 5%. So sum loss is not only giving you high performance, it's also more robust to learning rate, so you don't have to pick the exact right learning rate to get a good result. And then they also looked at how many number of epochs gives the best performance, and they found that 2 epochs is the best performance, and it degrades if you add more epochs to your training. So going back to takeaways for training, increasing model size and domain-specific pre-training improve downstream skills. The best single SFT run is used, because the soup isn't always the best, given different random seeds. And sum loss is used instead of mean loss. It provides more stable training, gives higher performance. So that is SFT. With that SFT done, we can now go into our preference tuning. So the model has already learned, it already has general pre-trained knowledge. Now it's learned from prompt response pairs. Now we want to introduce this idea of preference. All right, there's a lot of takeaways in this section. So first one is that length normalized DPO is used because it's relatively simpler and faster compared to PPO given their compute constraints. The prompts that are selected from the SFT mix. There's also prompts that were not used in SFT mix but were sampled for potential use in SFT. So those are unused SFT mix prompts. Those are also used for DPO. There are other sources outside of SFT mix, and they also add instruction following constraints to a prompt. For each prompt, they generate 4 responses from 4 randomly sampled models. They use both off-policy and on-policy data. So they use the Tulu 3 SFT, that's on-policy, and then they use other models that are off-policy. For those 4 responses per prompt, the LLM judge rates each response from 1 to 5 across helpfulness, instruction following, honesty, and truthfulness categories, and then they binarize that to get pairwise chosen rejected pairs. Scaling the number of unique prompts improves DPO performance. Duplicating prompts and then creating responses does not necessarily yield significant gains. Prompts that are not used in SFT but are used in DPO lead to higher DPO performance, but combining unused and used SFT prompts leads to best DPO results. And then finally, including on-policy data improves performance. So a lot to go through, but I find this figure to be very helpful. So here's the summary of prompt selection. We have some prompts that are used in SFT. We have prompts that were sampled from data sets that were going to be used in SFT, but we ended up not for whatever reason. So we're going to use those unused SFT prompts as well. And then they have some new out-of-domain prompts from ultra feedback and some persona prompts. We generate responses with off-policy models as well as our on-policy model. And then we annotate with GPT-4o 1 to 5 scores, and then binarize them into chosen and rejected pairs. They use the Argilla binarization algorithm or approach, and you start by computing the mean of preference ratings across your categories for each response. You pick the response with the best mean rating as your chosen, and then you pick a random of the lower mean values as your rejected. The DPO objective at the top is what they did not use. They did try it out, but they found that the length normalized version is what actually gives them the best results. And what that length normalized version is doing is that this kind of comparison between the model being trained, which is this pi theta is the model being trained, pi reference is the model that's the reference model, which is your SFT model, and you're taking the log of those probabilities and then multiplying it by a beta parameter. And here we're now dividing by the length of the preferred response, which is the C for chosen. And here for the rejected comparison, we're dividing by the length of the rejected response, which is R. They tried SIMPO, DPO, PPO, and DPO norm for a given compute constraints. and they found that DPO norm gives the best average score. They did say that if we use more computational budget or do more training, it is entirely possible that they can push up the PPO's performance even higher. A brief term definition: on-policy data is text generations from the SFT model that will be used as the base model for preference fine-tuning. This is different from online policy online data, which means that you're kind of using the live model being trained at each step and then generating data from here. On policy is a frozen model that is not being trained, but was trained with your SFT pipeline. This is the comparison showing that GPT-4o, when used as the preference annotator, yields the best final DPO results with an average of 57.3 across these benchmarks. And this is showing how they used some reused data. They used wild chat data. They used ultra feedback cleaned, and then they used this data set called Persona IF, which we're going to talk about as well. This is showing that as you increase the size of preference data, in terms of the number of unique prompts, the overall average, as well as skill-specific performance increases for their DPO pipeline. And this shows that when you have 64,000 unique prompts and then you duplicate them, the performance doesn't really improve, and in some cases actually gets a little worse. This is a reminder that in their dataset table, I think it was table 7, you have your count of dataset prompts, and then you have the prompts that are used in SFT and prompts that are used in DPO, and those numbers are not always the same, right? So we only use 10,000 of sci-riff in SFT, but we use 17,000 in DPO. And in some cases, we will reuse prompts that were used in SFT and use them in DPO, and in some cases, we will use prompts that were not used in SFT, but we will use them in DPO. And that was their approach. They sampled 100,000 prompts from the SFT dataset mix that were used during training and compared it against prompts from the same open dataset subsampled from but left unused during SFT, and they found that combining both used and unused prompts gave them the best results. So here's an example of kind of the intermediate results: DPO with reused prompts, DPO with new prompts, and the new prompts give a slightly higher score, and using both gives the highest. And then this is their evidence that on-policy data, including on-policy data, improves DPO performance, because off-policy is a bit lower than on-policy, which is a bit lower than combining both on-policy and off-policy data. Continued takeaways: SFT preference mix, which is their final mix, outperforms ultra feedback, which is kind of the open dataset standard. They found that including persona math and persona code does not improve math and code performance and actually harms average score as well. That was surprising to me, right? I did not expect that they would find that math and code data does not improve math and code performance, but in terms of preference, it does not. Persona IF improves IF eval and average score, and Persona IF is a dataset that took their original instruction following Persona SFT mix, and they turned that into a preference dataset. And the way they do that is that they add synthetically generated rejected responses that fail one of the constraints, and then that gets a lower score, and then that is used as chosen rejected pair. They also have this IF augmented dataset, which we talked about, which was starting with Tulu 2 SFT instructions. They add constraints, they add synthetic completions, and then they make a preference dataset with chosen rejected pairs. They expanded this, and then they also filtered it for verified responses to create IF augmented verified. So basically, verified responses means that the response did successfully include the constraint that was in the instruction. But that doesn't improve performance. So ultimately, they use Persona IF and IF augmented They also use wild chat prompts and synthetic, and they find that improves performance. And then interestingly, synthetic regenerations of datasets. So using the same prompts, they regenerate synthetically the completions and preference annotations. That actually improves performance. And we're going to take a look at each of the charts that support this with evidence. So here's their evidence for their best mix on DPO, beating out ultra feedback on DPO, both for 70 billion models and 8 billion. Here is their evidence that Persona IF improves the average, but Persona Math and Code decrease the average. Here is the evidence that Persona IF improves the instruction following eval score, but Persona Math actually decreases the math score, and Persona Code 81.9 decreases the 86.1 baseline. This is showing that when they have their IF augmented dataset included, when they add Persona IF, they get the highest, or not highest, but they get an improvement in IF eval, and they get the least decrease in the average. So adding the augmented verified does actually improve IF eval, but it decreases the overall average across the other benchmarks. And then this one, I think, was the most interesting, which is that regenerating using synthetic pipeline yields better performance than using the original dataset. So that was a really interesting one to see and speaks to the power of synthetic data. Okay, to recap, preference fine-tuning takeaways. I'm only going to go over the highlighted ones. Length normalized DPO is used. Off-policy and on-policy data is used. GPT-4o is the judge that annotates the preferences. Scaling the number of unique prompts improves performance. Combining unused and used prompts from the SFT mix leads to the best result. Including Persona Math and Persona Code does not improve math and code performance and harms the average score. Persona IF, which is their preferenceified IF Persona SFT dataset, plus IF augmented improves performance. Wild chat prompts with synthetic preference data improves performance. And synthetic regeneration of datasets, where you have synthetic completions and preference annotations, improves performance. Some training and infrastructure takeaways. For 70 billion sized models, they pre-compute and cache the log probs across the dataset for the reference model. So if you recall the DPO equation, the denominator inside those logs was the probability generated given the response, given the prompt for the reference model. And so that's the reference model log probs that are cached beforehand, so that you don't have to store the model in memory to generate. They also separate the forward passes for chosen and rejected sequences, which seems like that's the norm, is to combine them. PPO gets similar average scores with DPO. PPO is more computationally expensive, 7 times more in terms of time. These are the learning rates they found for the 70 billion DPO model with different mixes. And then these are the final DPO training parameters with only one epoch of training. Okay, so that is stage 3, where we are teaching the model preferences. And now we are entering the final stage of training, which is reinforcement learning with verifiable rewards. Again, as a disclaimer, this is not my strongest point, so I cannot go as deeply as I did in the other sections. So these were my RLVR takeaways. The main thing being that they're replacing the reward model with a function, right? So it's a lot more lighter. The data then becomes prompts along with some verifier function, and we'll take a look at that example. For GSM-8K and math, they want to encourage chain of thought, and then the verifier function extracts the final number from the response. For instruction following eval, they have instructions, they have constraints, and the verifier function is then seeing if the constraint is met given some template. And the template is things like number of words or capitalized letters or asterisks and so on. Models are trained using PPO with dropout disabled. They shuffle their epochs, and they have a EOS penalty, non-EOS penalty. So if the model does not generate an EOS token at the end, it gets a penalty for that response. They find that RLVR improves targeted domain performance, and they find that more KL divergence typically results in lower average scores. My understanding of KL divergence in this context is that how far from the distribution of tokens are you diverging from the base model or the reference model that is not trained on reinforcement learning. So it's another way of saying, I think, that how much of the base skill are you losing? And not only does more KL divergence mean you're losing base skills, overall average scores decrease as well, including those other skills that you're trying to learn. This is a pretty diagram that I wanted to include. You start with your prompts. You feed that to your policy. It generates completions, policy model. You throw that into that completion into the function that verifies whether it's correct or not. If it's correct, it gets a reward, which I think was 10. If it's not correct, it gets 0. So it's a scalar reward, and you continue your training. These are the data sets and domains that they performed reinforcement learning for. The verification for GSM-8K in math is an exact match. The verification for instruction following is prompt-specific verifiers, so based on the constraint that's being tested, verified. This was an interesting set of charts that show the KL divergence increase leads to a loss in performance on average, and in some cases a loss in target performance as well. So GSM-8K performance decreases, math performance decreases, IF eval performance actually kind of stays the same, but in every case the average score drops as the model diverges from the reference model. Here this is showing that Tulu 3 RLVR beats out DPO overall, but there are some cases where the DPO model actually had slightly better performance. And we see that for 70 billion, we kind of see the same thing. Overall, RLVR beats out DPO as well as Llama 3.1 Instruct, but in some cases, when you look at granular data across categories and across benchmarks, DPO and Llama 3.1 Instruct is slightly better. This is an example of the model over-optimizing to the reward. So this is like reward hacking as an example. Measure the length of the given object in centimeters. Pen. Include keywords timber-like, comma, unconnectedly in your response. So the model just includes timber-like and unconnectedly. It ignores measuring the length. Same thing here. Measure the length of the given object in centimeters. Pen. But the constraint is include the word crespidodromus 25 times. So it does that. Or here, it ignores the instruction except the verifiable constraint, which is that in your response, the letter E should appear 14 times. So it does appear 14 times. And there was a particular beta value for KL divergence that was associated with that. And a different beta value leads to better results. In this case, the model does talk about measuring the length of a pen, even though it hallucinates a pencil, and 15 to 20 centimeters. It does include timber-like, and it does improve unconnectedly. Same thing. At the bottom, it includes the typical length of the pen. Standard pen is typically around these many centimeters, and it does not include the keywords loath, Asclepius, cardiosynthesis in the response. So here now, it's not over-optimizing to the constraint, and it's answering the question, and it's also following the constraint. And then this was performance on different starting points. So if you start with the SFT model, you generally get lower GSM-8K performance. You get lower rewards, and you get higher KL divergence. If you start with the DPO model and then do RL, you get higher performance and accuracy, higher rewards, and lower KL divergence. This is an example of one of their verifier functions. So it's called it has a parse completion method that extracts the reasoning and score from an OpenAI API completion response. And if there is a completion, it grabs the message content and passes it through this extractor, which returns reasoning and a score. If we look at the extractor is any number of functions based on the goal or based on what's being checked. And one such utility was extract score from string, where it takes the string in question from the response string, and then it does a regex search, and then it returns, whatever the actual numerical value is. So just a quick peek into what these verifier functions look like. Next, we're going to look at everything that kind of ties together the previous 4 stages, which is the Tulu 3 evaluation framework. The framework is called Open Language Model Evaluation System, OLMES, and it's released publicly. They have a development eval suite and unseen eval suite, and they both contain different data sets. The guiding principles for the unseen eval suite is to formulate tasks similar to how humans interact with models, prompt models with clear instructions, and apply reasonable answer extraction heuristics. They innovate 2 different unseen eval benchmarks. One is called Instruction Fine-Tuning Eval Out of Domain, where they create new custom 52 constraints sourced from these authors and other researchers. And then they have HREF, which is an automatic evaluation on high-quality human-written prompt responses using a win rate against a baseline model similar to the Alpaca eval framework. The main takeaway from this section was final checkpoints obtain best average performance on both development and unseen evals. And what that shows is that the design decisions did not overfit to the development evals because they had the best performance on the unseen evals, and we'll see that in a second. SFT data ablations average is highest for final mix for both development and unseen evals. Increasing data mix improves both averages. And when you compare the results of other models on the unseen suite, there's mixed results, but that may be because the unseen data sets are in the training set of these other models they're comparing to, which we can't confirm because we don't know what data was in these models. So, looking at the evidence to back up these claims, 8 billion final has the highest development and unseen eval suite. And not only that, if you look at SFT, DPO, and final, in each case the development performance increases and the unseen performance decreases. So all design decisions at each step are improving the generalization from development to unseen. If you look at the intermediate scores, there is some diversity. So in some cases DPO had a higher score, in some cases SFT had a higher score. And we see the same pattern for our 70 billion models. When we look at the data decisions made, so including wild chat, including safety, including persona data, including math data, in each case, and in terms of the overall average, I guess, not in terms of each case, but in terms of the overall average, the development average and the unseen average is highest for the SFT model with the final mix. Removing wild chat decreases the averages. Removing safety decreases the averages. Removing persona data decreases the averages, and removing math data decreases the averages. So all their design decisions when it comes to data mixtures yielded the best performance on the unseen data, which means they did not overfit to the development suite. This is the comparison of different models on the unseen suite. So Llama 3.1, 8 billion instruct, Hermes 3, Llama 3.1, 8 billion. Tulu 3, 8 billion, and Tulu 3, 70 billion falls between those two. But again, without open training data for any of the other models, we cannot verify that those other models are not training on any of the unseen benchmarks. And then here, finally, we see that scaling the size of the preference data set when it comes to the unseen development suite, unseen eval suite, improves the downstream performance. And this was for DPO. All right, let's go to the last section where we're going to do a little bit of highlights from their discussion and conclusion. Here were their discussion takeaways. Their 405 billion model was trained on 256 GPUs in parallel. For RLVR training, the inference step was about 10 minutes, weight transfer was half a minute, and training was about 15 minutes, 20, 25 minutes. And their future work is to utilize GRPO as the algorithm instead of PPO. because of compute constraints, their hyperparameter tuning was limited, and the RLVR training ended early. Online DPO, which is different from on-policy data, did not improve results. So online means you're sampling responses from the policy model as it's being trained. And rejection sampling does not improve results as well. Future work is long context and multi-turn conversations, multilinguality, and tool use and agents. And to conclude, Tulu 3 bridges the gap between open and closed post-training methods, marking a new milestone in open post-training research. With the resources provided, others can build on open-based models, fine-tune them for high performance across diverse tasks. This paves the way for advancing post-training research within multi-objective and multi-stage training frameworks. So, as you can see, very information-dense paper, but also very accessible. They were very clear in spelling out what worked, what didn't work, and then backing up those claims with evidence. Usually, when I'm reading a paper, I will circle the paragraphs that I want to include in my slides. And this was probably the first paper, if not the first paper in a while, where I found myself circling almost every single paragraph that was in this paper because I felt like I could not leave that out of the presentation. So this paper is certainly in my Hall of Fame of papers. I think it's, sets the standard for what open research should include. And I think that this is motivational for people like me because now I know what is the standard for training, but also what is the standard for setting this information out in a accessible and information-rich way. So I hope you enjoyed this slideshow and this presentation on the Tulu 3 paper. I highly recommend reading the Tulu 3 paper. You simply cannot summarize it. You have to kind of read it and see the story unfold in the way that they have described it. So thank you for watching, and I will see you next time.